Just the white balance. Lock that, actually. There. Okay. All right, so today, what we are going to focus on is structured text. It's the first of the 5 or so languages that we're going to cover in the course, and it is pretty easy, I would say, to get a hold of. The few things that we need to know is how to assign variables, how to do math, and how to interact with our inputs or our outputs, also known as I/O. Right? You guys have seen I/O before, inputs, outputs. So I'm going to show you guys a basic idea of how to do each of these things. Okay. Do I have an example? I don't have an example of structured text. This is too complicated to show in the first example. Okay, this is great. This is excellent. Everyone see this okay? Okay, this is a program. It does something meaningful. It says written in structured text. That is the language, the code. Okay, the way that structured text works is very similar to Python, to Lua, to C and C++, pretty much any scripted language, right, where it runs more or less sequentially, where we hit this line, evaluate it, do what it says to do, then we go to the next line, do that line, the next line, do that line. It's not an interpreted language, it is a compiled language. You guys know what that means? If you don't, that's fine. What happens is when we step through this code and imbue meaning in it, we use English to establish logic, right? If this, then that is literally something that we can write down and really get like 90% of the behavior of our program. Like, if this is happening, do this. And this is how, for example, we can take an input, evaluate if it's high or low, and then do something accordingly. Is our switch on or off? Is our sensor reporting high or low, right? And then turn a motor on, turn a siren on. So what this is saying is if this variable, this is a variable right here, literally if start PV, so this evaluates to if variable. Okay, so our variable right here is called start PV. This evaluates, it turns into literally a 0 or a 1, depending on what is stored in that variable, okay? So that variable could be manually written to it, like we said that somewhere in our program, high or low, or something from the outside world might be setting that high or low in terms of an input, right? If like we have a level sensor, water in a tank, right, trips our sensor, now we're saying if that sensor is reporting a 1, then do this thing. Okay, so here's an example of how we create an output in our world. Okay, we can specify certain variables. We can tell the program, this variable means this output. When I set this variable high, we're also turning on our output or turning on our relay, right, making that connection. This is how we assign something in structured text. Really the first and most important lesson of structured text, it's not simply equals like it is in a lot of programming languages, right? In Python, when you're setting a variable equal to something, it's equal that thing. It's colon equal that thing. It's kind of weird, but that's just what it is. If you don't do it this way, it won't compile. It'll complain at you, and it won't get where you want to be. Okay, also notice that at the end of these lines, not all of them, for example, these thens are not terminated by semicolons, but these are. Okay, so for example, Arduino also uses this same line ending, okay, where it's terminated with semicolons, and if you don't have a semicolon, you'll get some weird errors and it will complain at you, it won't compile, or it'll have some weird behavior, okay? So please note this down, take a picture of it, or do a very simple note, because this pattern can get you so far. If this, then that, right? If you just keep chaining these blocks of, they're called conditionals, okay, if this thing, then that thing, and then cover the next case, and the next case, and the next case. It can get ugly, but you can create perfectly usable code, right? Perfectly functional device. Yeah.
For structured text, do we also define the variables there, or?
Yes, you can, and I'm going to show you that next for sure. That's a good question. So there's actually two ways to define a variable, and I'm going to show you that, assuming this is finished compiling. Okay, it has. Great. So if you're done compiling on your respective PCs and you can interact with the software again, we're going to go over here to resources. Okay, I know this is a lot visually. It's a very busy program. Okay, but try to look through the noise a little bit. We're going to go over here. We're going to go to programmable inputs. Okay, this is where the rubber meets the road in terms of assigning variables to like physical space. Okay, so you guys remember that our inputs to the device are where our sensors go is on the top of the device. All of our stuff goes in the top and it goes out the bottom of the PLC. Okay, so also note, please look at your PLC and see that I1 through I8 is printed on there. Right? You guys also see, I hope, inside of our programmable inputs mapping list, we also see I1 through I8. You can probably see where this is going. Go ahead and open up the software on your PC over there. So what we can do now is we can assign variables. You can double click on a space and you can call it whatever you want. You can call it bread if you really want to. But you just have to use that term everywhere. It has to be spelled exactly the same. Okay? I believe capitalization also counts in some cases. But it's just simple, human-readable, whatever. Okay? You could name it motor, siren, beeper, right? Like whatever is actually attached to the relay or the sensor. Whatever makes sense to you because you're going to be using it in your code. Okay? This is just to show you that I could now use that variable. So for example, here, if count, I'm setting count is equal to count plus 1 in this program. This is the default program that's on the device. All this does is take a variable count, CNT, and it increases it by 1 every loop. And then it runs that script over and over again. You guys might imagine that what that'll do is that'll keep increasing count over and over and over and over again until it hits a theoretical upper limit and it wraps back around. It goes to negative, I think, or 0, right? And then just keeps on counting. Okay, that's all the program does. It's essentially a canary that shows us that the PLC is still running and doing something at all times. Okay, default program. Now, if we say, for example, if count equals 100, okay, equals is reserved for the comparison. Okay, this is why we don't use it as a, yes?
How'd you get into that if count screen?
I double-clicked on main right here. So this is how we edit a program. I'm just showing you this as a for instance. You don't actually have to follow, just like it. But okay, so we're saying if count is equal to 100, for example, then we want to say then, this should also be capital, then bread equals 1. A little silly, but you guys understand that bread is attached to my terminal, right? And if I set that equal to 1, then the output will go high. And if I set that to 0, the output will go low. Okay, I actually made a mistake just there, sorry. Not to confuse you guys. This is in the programmable inputs. But if I wanted to control a relay, which is kind of what I was actually showing, I'm going to move, let's see, I said bread. Okay. So I'm going to take my bread variable, and now I'm going to attach it to a relay. Okay. So sorry if that's confused you, but we jumped down to our relays on the bottom here. Okay, now we're assigning variables to our relays. If we set these variables to 1 or 0, we're now triggering our relays to turn them on or off, to make them open or closed, right? To attach one of these terminals to nothing, or to attach it to a power supply that'll theoretically turn it on at whatever voltage is on our other terminal. Right? Does relays make sense to you guys? You remember that from the last class? I'll probably revisit it in a second, but I just want to make sure we're kind of tracking. Right? Any questions so far?
I pulled a little quick maneuver on you, so I don't want to make sure I didn't lose anybody. Are we tracking with the variables and how we assign them and what this actually means? Great. Excellent. All right. So this is, again, one way that we can assign variables. We can assign them to our inputs, our outputs, and there are also onboard LEDs. Okay, there are 4 LEDs. They're green, 1, 2, 3, 4 in the lower left. You can use those however you would like. Typically in this class, we use them to visualize the status of the relays, because the relays don't have like an LED that's tied to them like specifically. You would have to program it that when we turn this relay on, we also turn on this LED. Okay. Otherwise, the only thing that we could tell that the relay is working at all is if our thing turns on that we attach it to, or if you listen to it click, you can actually hear it click on and off. But otherwise, without that LED, we have no idea. Okay, so if you wanted to do, for example, if my relay 1 was a motor, I might call light 1 motor LED. Okay, and now whenever I set motor LED equals 1, that LED will turn on. Motor LED equals 0, it will turn off. Okay. We also have a user LED and a user button. Okay, if you look on your PLC, it's a general use button right here. It doesn't actually do anything by default. It's entirely up to us to assign behavior to it. Right? It might kick off your process. It might make an LED blink. Who knows? Who cares? It's totally there just for your convenience. Above that LED is an RGB LED as well. Again, for whatever purposes you deem appropriate. It might blink, every once a second to show that the device is alive, or it might, respond to a sensor input. It's entirely up to your discretion on how to use it. Please do so at your own benefit and convenience to make your life easier. Okay. A lot of what we're going to be doing in this class is just debugging. It's not outsmarting yourself or making a dumb mistake and not being able to find it. So having an LED that turns on and off when appropriate, having these indicator lights that we're talking about with our relays, making that good practice to use that during this class. Try to make that a part of your workflow. Keep it in mind as we're going.
I'm sorry, how do you open the IM
So you probably need to make a new project. New project, right?
Yeah.
And then you can go to right here in resources. The lower left tab, I think. If you have any questions, let me know. Anyone else? Any questions? So far, so good? All right, cool. So, other thing is this is our button input. Okay, so theoretically, we could have a button that is like a button in the real world that's attached to a remote and has wires coming out of it, right, that we could put into the input part of our PLC. And we could sense, whether that button was pushed or not by querying our inputs. Okay. That is not what this button input means. This button input is very special. It's literally for our button that I talked about before. This is doesn't have anything to do with the actual inputs. And when we're wiring buttons and switches and stuff in the physical world, those still go in the programmable inputs. Okay, the button literally just means the button that's built into the device. The rest of this we don't really have to worry about. The only other thing that I would like you to know is that this is where the Arduino stuff lives. If you know Arduino or are interested in looking into it, by double-clicking Sketch, this is how you access the Arduino programming bit. So if you write Arduino code in here, when you compile and upload code to the device, this will go to the Arduino coprocessor, and then the PLC code will go to the PLC processor. And then they can share variables and crunch data and do cool stuff like that. But that we'll get into later in the class. You guys will be plenty comfortable with the program by the time we even start to get into any of that stuff, so no worries. Okay, so ready to make our first program? See what's going on? So first, we need to connect our devices. So please get your PLCs connected through USB-C. And also, we won't power them just yet. So just make sure they're powered through USB-C. Yeah.
It doesn't matter, it says different port.
Different COM port?
Different port.
plugged in, but it still says not connected.
Oh, diff code, yeah, that's fine. That's fine. As long as you have connected.
Yeah, I plugged it in, but it says not connected.
So you still have to go to online and then connect to the device. Right, you still have to go through the connection process. So online, and then set up connection, right? Go to properties and set your COM ports, just like we did before. Yours will be different. Yours will be like 3 or 8 or 9, whatever. Click OK, OK. And then when you go to, eventually, when you exit out all that and go to online connect, you'll get the green connected to the bottom right. Okay. If it says diff code in yellow, that's okay, but we want it to stay.
Sorry, I'm late.
Oh, no worries. Well, you did just miss a big explanation, but it'll be on the video for later if you want to recap it.
Thank you.
Quick recap on everything that we've done so far. 30-second recap. So actually we'll be able to bring up to speed pretty fast for the rest of you guys. It should be good practice. So what we did, I'm going to exit out of this. Okay, so I went to the Arduino PLC IDE. We will use the blue icon later, but again, that's later in the class, like week 7 or 8 or something. So we're only working with the Arduino PLC IDE. All right, we're going to get this launched. We're going to go to New Project. Each lab will be its own project. Okay, each project might have more than one program. Okay, so you might have like subsections or maybe multiple programs to get like one behavior, and sometimes they can work in tandem, right? So we're going to make a new project. Again, you guys would do something like your last name, Modrich _ ELT240 lab 1. This is the second time I'm doing it, so I'm just making a unique name, saving to the documents folder, and by default out to 1.2. Bam. All right, so far we've talked about programmable inputs, right? Our I1 through I8, which is the top of the device, how we can assign variables by typing in unique names, and wherever we use that name, we'll talk to that input, right? So for example, if I have an infrared sensor, it's measuring the amount of infrared light that's hitting it. Maybe there's a laser going into it, and when we block the laser, we don't see that light anymore, and we're doing something with that input. We're checking to see if it pulses or if it's high or low, whatever. If I know that that input is on input 2, there's a physical wire that's going into my device, and it's attached to I2. I can just call that IR laser. Okay, and wherever I say in my code IR laser equals 1 or IR laser equals 0, I am checking something in the real world and acting accordingly. Our outputs is how we interact with the world. Okay, and we've read our laser, now we want to do something. Say I have a motor or a fan that's going to kick on. Okay, I have it attached to my first relay. It's a 120 volt fan, so I've got 120V coming in on this terminal. It can be AC, by the way. Relays can do AC or DC. It doesn't really care. One of the cool things about relays is that unlike transistors, relays are, to the electricity, they just appear like a strip of metal. They have no problem shooting across there. It doesn't care if it's AC, going forwards, going backwards, doesn't matter. It just matters that it's not too much power, right? That we're not shoving too much power through the relay that we're going to melt these contacts together or something crazy. And that it is not high enough voltage so when these are separated, if it's too high voltage, it will bridge the gap anyway, right? Even if those contacts aren't closed. So there's a voltage rating on these devices. All right, but we have a fan on our first relay, and now, just like our inputs, when I say fan equals 1, literally in the code, one line that says fan equals 1, it will turn on our relay, it will close those contacts, which will expose the fan to 120 volts and turn it on. Okay, good review? Everyone on pace? All right. For you guys, make sure you hit this button up here in the upper left. That's the compile button. It'll take a while on the first go, but after that it'll be relatively fast. Okay. That first compile process is for every new project. I'm pretty sure it like saves the files in your project folder, so you don't really have to do it again. But so we'll pretty much just have to do that like once every class kind of thing. Load up your program, hit compile, you know, when you show up, and then by the time we're ready to go. Yeah.
Would you mind showing me how you would connect to your Arduino again? That error code, trying to connect to it?
Sure. Yeah. Let me get you sorted. The software can be finicky sometimes. So.
And you were saying something about setting up communication.
Yeah. And then go modbus properties. Yeah, okay, so change your port from COM1, change that to COM9.
So it would be on that?
So it'll be 50-50 shot whether it's 8 or 9. Or PLC. And then, oh, there we go. Good stuff. Yeah. Okay, so anyone not connected? Not connected. All right, I'll give you guys a little bit. Just sit tight. All the rest of you guys have a green connected in the corner. Yeah. Okay. All right. So let me see if I have a cable myself. Hold on.
Just found one.
What's up?
Just found one.
Oh, good. Okay. Hopefully this isn't a charge-only cable. Okay. Okay, I'm just gonna have to pretend for a little bit. All right. So, what I wanted to show you guys next actually can be done with the main default program. Okay, so if you guys see what I did, I went over to the project tab, switched over from our resources tab, different tab, project tab. Double-click main to open it up. Now this is our program. All right, we can modify it if we want to, but I don't want you to. I want you to keep it as it is. Assuming you compiled this already, I'm not going to compile it because I think it would recompile. It'd take a while. What I want you to do next is to actually upload the code that is compiled and living on our PC to the device. The way that we do that is with this button right here. See how it says download PLC code? Okay. So what that's going to do is it's going to push the device that is now compiled on our PC and burn it onto the PLC. We can do that over and over again. It's not like a one process. What's up?
I got a pop-up saying cold restart required.
Oh, you can click yes. If it says cold restart, you can click yes. It's just saying that it's going to reboot the machine when it uploads code. Yeah, so it's going to burn firmware onto here, which means that that code now lives on here forever. It can power cycle, right? Get hit by lightning, as long as it survives, it'll still run that code. And every time we re-upload code, it overwrites the previous code. Okay. What else do I want to talk about? Yes, when you click download PLC code, you don't have to recompile. Okay, it automatically clicks that button for you. So if you change your code and you hit download PLC code, it hits the compile button for you to recompile the code and then push it to the device. Okay, so it's not like you're going to be uploading old code or something weird like that. The yellow diff code that some of you guys see right next to the connected is just telling you that the code that you see in your window is different than what's on the device. Okay, that's kind of the mental check. Hey, what you see in front of you needs to be uploaded to the device because you know what you might be debugging isn't actually even running. Right, that happens sometimes too. Okay. Talk about more things. That CNT variable, okay, where we are storing the number that we're counting up over and over and over again. Okay, that number is stored in our global variables right here. So I double-clicked on this flag, and now we have, essentially it's like a mini Excel sheet that we can stick variables into. Okay, so I can right-click here and then click Insert, and I can create whatever helpful name I want. Okay, they can be helper variables, storing useful bits of information, right? They might be like a conversion unit, right? If you're converting Celsius to Fahrenheit, you might have like, a weird number stuck in there for doing math with. This is where we can put really anything we want. Global means that any program we make, so if we make a program other than main, if we had some other programs doing things as well, they could also see what's in here. Okay, so if we had like a master state variable, like run or stop, and we wanted all of our programs to see that variable and respond accordingly, we would want to put that variable in the global variables, because then every program could see it. Okay, as opposed to local variables. Okay, so inside of our program are local variables. Okay, so right above our window here. Okay, you guys see as we're opening windows, we also have these smaller tabs down here. It's easy to get lost in this program. Okay, so inside of our main program, we can create local variables, just like we made global variables right here. We can right-click and insert. The thing is, local variables are unique to each program. Okay, so if I had a speed variable, if I had 3 programs and each of them had a speed variable, okay, it would only tell the information in each of their speed variables. They wouldn't see like a master variable or wouldn't share information. Okay, does that make sense? Local versus global scope. This is programming scope. Have you guys encountered this before? Does it not make sense? Does it make sense? Okay. All right. I want you guys to delete any variables that you made. We're just using the global variable count. Okay, see here we can right-click and delete variables. We're just going to have count. You can have ham or whatever, it doesn't matter. So we're going to connect if you haven't already, and then download PLC code. And then it'll push the code. You should see 2 green blocks in the bottom right. Okay. Yeah.
We have another cord.
Don't. Are you down a cord? I think I thought I had a loaner cord in there. Or we always seem to lose a cord every semester. I gotta get extras. Does anyone have a USB-C port, like in their backpack or something that you know that'll work? Anyone will work, yeah.
I could try this one then.
Okay. Thank you, let me know if you have trouble. But yeah, any USB-C should work. Okay, so hopefully a bunch of you guys should have 2 green blocks, okay? Meaning that we're connected to the device and that the code is the same. And now we can do something pretty cool. This is one of the most powerful aspects of a PLC, okay? Again, microcontrollers, $5 boards can do what a PLC does. Why do people still use PLCs? It's because they're easy, they're really reliable, they're easy to maintain, and they have awesome debug modes like this. So if you guys click this button that my mouse is hovering over here, this is called live debug mode. You'll see what pops up right next to the variable is a live preview of the current status of that variable. Okay. I'm getting less oohs and ahs than I thought. Are you guys doing it?
Yeah.
Getting a negative number, it's counting down, is that normal?
Yes. You didn't upload code. Oh, yes.
It says no code down here.
Yeah, I've had this issue before. Can you, you might have to restart your program too. We're going to try this one. Go ahead and connect to it here. can you restart the program and try to re-upload to it? You're doing everything correctly. It's just I think the programmers would be honest. Yeah, let me know if you're still having issues. Anyone else not able to see the count moving, changing? You guys, you're okay? So, so click this button that uploads the code. Yes. So what that did is it's compiling the code, which means that it's on the PC, and then it will upload the code, which means that the code will be on here. And then once it is, it looks like you didn't do the compile sketch earlier. So that's why I said to click this button earlier, because this is going to take a few minutes. So once that's done, it should upload code, and then when you hit this button, like you were trying to hit before, you'll actually be able to click it, and then you'll see more come up. Yeah. Anyone else? Any questions?
Yeah, I still don't have it.
Still don't have it. Okay. I might have you move over to this PC then, actually. Is that okay? Just over to this terminal. You can take your PLC and everything. It's just a different computer. All right. So now I want you guys to take a couple minutes and mess around a little bit. Make new variables, increment them in interesting ways, multiply them, divide them. Okay. I'm going to show you one more thing while you guys are doing that and messing around, and that's talking about how programs run in PLCs. Okay. So they actually run at different rates that we define. So there's 3 different groups, pretty much, well 4, right? Fast, slow, background, and init. Starting at init, this is what happens when the unit first comes alive. All right, it powers up. This is the very first thing that it does when it can possibly do something. And it only runs it once, right? We're kicking something on or setting something up, right? Moving variables to and fro, maybe sending off a communication message saying, hey, I'm alive. And then that's all the code does. The program just runs once. Background runs at 500 milliseconds, right? See, the unit is milliseconds. So every half of a second, this task will run. Okay, it's not very often at all. Typically, this is like a task that we either moves really, really slowly, right? Something that changes not very quickly. Maybe some math that doesn't have to be crunched very often. And then we have slow tasks, which take 1/10 of a second only. And then fast tasks, which take 10 milliseconds. Okay, we can essentially do anything that we put in this fast task group 100 times a second, right? Every 10 milliseconds, we'll be doing that task, okay? Notice that by default, our main program is inside of the fast task group. That means every 10 milliseconds, roughly 100 times a second, we take the variable count and set it equal to itself plus 1, okay? And then 10 milliseconds goes by, and then we do it again. 10 milliseconds goes by, and we do it again, okay? So that's essentially how this works. So it will run line 1, there's nothing on there. 2, it'll do it. 3, there's nothing on there. And then it'll do it over again, and over and over and over and over and over and over, okay? So by putting different programs in a combination of fast and slow and init, it worked that time?
No.
Okay. Okay, 1 second. So by putting, for example, things that need to run really often, right, like real-time processes in the fast task group, almost everything we do goes in the fast task group, or lazier processes or things we don't really care about updating really fast, or computationally intensive processes in the background task, right, that runs half of a second and doesn't really care about timeliness, okay? Think about that, really important. If you accidentally, or on purpose, who knows, delete a program from that fast task group, it won't run at all, okay? You could compile it forever, and it will never actually run and do anything, okay? It's still on the device, it's still here, right? We can edit code in our main file, but it's never actually being called. It's never actually activating, right? The device needs to be told how often and how fast to do it, okay? So whenever we have programs that we need to run, we need to drag them, or upon creation, right? When we're adding new programs, we assign them to a group right at the start. Okay, by default, be careful, it doesn't assign it to a group. You could, easily have it not running at all. make sure you put it in the appropriate fast, slow background or init group, usually fast. Okay. All right, I'm going to take a beat. Feel free to mess around with, creating new variables, adding them, multiplying. Again, remember, whatever you guys do in terms of arithmetic, it's going to do it 100 times a second. So if you're multiplying count by 8 100 times a second, that number is going to whip around pretty fast, right? Where if you increase it by, like a fraction of that amount or something more reasonable, you might actually be able to see a change. You could do things like sine waves or ramps, right? Play around with it, see what comes out of the live debug mode. Okay. All right, I'm going to come around, help those who need it. What's? Oh, you're just compiling. Okay.
Yeah, we'll see if it works out.
I think it will. I have a strong feeling it will, but hopefully it will. Anyone not getting? So, think.
Yeah, I just want to get that up there. I just missed that part.
Oh, no worries. Yes.
Yep, connected.
I think you just need to upload it. So it's actually just this button. So this is the compile and upload button to the right. Yes. So that'll do it. There you go. Yes. That's compiling. Is this the first time you're seeing that?
Well, I did see this earlier. I didn't hit that button. I hit just compile, and it read the same line.
Okay.
So that's why I restarted.
So this should be a little bit faster. I think it's not the first time. So what that button did is it compiles, which is a long lengthy process, and it'll upload code, and then you can click this button, live debug, and then we double click on the main program.
Great. Are you going to go over the lab objective, or have you already?
Yeah, so I actually still have the lecture to get, which is
Sure.
like all of this stuff.
Yeah.
Then there's like a write-up on the protocol.
Okay.
If you guys want to bring up the protocol, feel free to do so. It's on Blackboard.
All right.
Week 2, lab 1. That's a good intro, actually. Good idea. So, we're going to go back a little bit. Got ahead of myself just a little bit, a little excited. But this is going to fill in some of the backgrounds that I just told you about, reiterate a little bit, and have some nice pictures to look at too. Okay. So, this is actually a really good segue, timed as well, in that what we were just talking about, right, putting things in those task groups, fast, slow, init, whatever, is the rate at which this scan process works, okay? So PLCs are also a little bit different from traditional microcontrollers in the way that they handle their inputs, their outputs, and their programs, okay? Typically microcontrollers, like your Raspberry Pis or your Arduinos, just kind of work as fast as they can, right? It runs the code in a loop as fast as it can. When it hits the spot where it's supposed to check the input and grab its state, it does just that, and it takes like a number of milliseconds to do that, right? And then it goes to the next process, and that takes a number of milliseconds. PLCs aren't like that. They're actually very rigidly structured in that no matter where your program says to read an input, for example, it can say it on the first line or it can say it on the last line, the input reading step always happens in a defined part of the cycle. It always happens before the program evaluates and before the outputs are adjusted. Okay? So again, in a typical computer program, you could, write all your outputs, then check your inputs, and then do your processing if you wanted to do that way for whatever reason. PLCs are very rigid in that the first thing that it does, for example, you power it on, literally the first thing that it'll do is it'll read its inputs. Okay, it'll take the current status, whatever voltage happens to be on each of those pins, and it says that's high, 1, or that's low, 0. That's where we're getting our programmable inputs from. Remember where we were assigning variables? So this is where the computer fills in those gaps, right? It kind of sticks each of our variables and the memories that it needs to have for those. Okay. Next, we run our program. So if we're doing things like saying variable 1 plus variable 2 equals variable 3, okay, that's where this step will happen. All of that stuff gets evaluated in one go. Okay, things to note, if you set something higher in the program, for example, x equals 1 on line 1, and then later on line 50, you have x equals 0. Okay, the outcome of running that whole program will be like the end result of running that program. Okay, you know what I mean? So if you set it 1 first and then later set it to 0, it will still be 0 at the end of all that. It kind of literally runs through the script, and what everything is at the end of running that process, that's what it is. Okay, that's why we do this step before the outputs, because we need to evaluate what those outputs should be at that given time. Right? At this slice of time, our inputs were this, so our output should be this. Okay? This is the scan process that happens at whatever rate we've defined. Once a second, or sorry, 2 times a second, 10 times a second, or 100 times a second. The PLC scan process. Okay? All right. Up here is a little bit more complex code. Okay, can you guys see this? I know it's a little bit small. If you're struggling to see it or just want to refer to it later, again, it's on Blackboard. PowerPoint is up there. All right, so follow along with me here. This is going to show you some examples. Please don't be afraid to refer back to this. Okay, if you need to know how to spell something, how to work with greater than, less than, really good reference right here. Okay, so our first one right here is a simple counter. Okay, maybe we are setting a counter in our slow task group that it counts up 1 every half of a second. And then we say, okay, when that counter hits 10, we do something meaningful. So we say if our counter variable, which is counting up once every half second, is less than 5, so essentially while our counter is less than 5, then do this next line. Okay, worth noting, we do not care about white space. What white space is in a programming language is invisible characters, spaces, tabs, indents, new lines, right? The program doesn't actually care about that. The compiler throws it all away. It doesn't see it. Okay, for all it knows, all it sees is one big line of text separated by semicolons. Okay, and that's kind of how it chunks it up. That's why semicolons are important, because that's how the computer reads it all. How it makes sense of one big line of code. Okay. Also in here is comments, which is nice to see. So this stuff next to here isn't included in the code. It's just human readable for your coworkers or for your future self or whatever. Okay. Each language does comments in a different way. We'll see comments later on, but they're just notes to the author. Okay, they aren't meaningful, they're not functional, so anything within here is not going to be evaluated. Okay. So if our counter is less than 5, we increase the counter. Here is something new. This is called else if. This is how we can check multiple things in one tree. Is this thing true, or is this thing true? If neither of those things are true, do this other thing. Okay, that is the if, else, and if conditional. That's like the full thing. Okay, which means that you can do something. If that thing is not true, you can check to see if something else is true. Okay, so it'll always run this one before this one. Okay, if this one is true, it doesn't care about this one. This only fires if this one is not true. See how that would exit out early and this would never run? If you always wanted to check this one, for example, this didn't care about what this was, you would just use another if statement. Okay, that's the difference between else if and just using 2 different ifs. Okay, else is kind of like the otherwise, right? The unhandled conditional. We said if our counter is less than 5, well, what happens in any other case? What if it's negative 100? Then we would fire this line. Okay, that is the else or the otherwise statement. Okay, if, else, and it always ends with the end if. It gives a very confusing error message if it does. Okay. Worth noting, if you do get an error message, for example, I forget a semicolon and I try to compile, we'll see an error just like this. See how it says syntax error? This is our debug output. Okay, it's a clue by the compiler. It's not very helpful, but it's telling us that something related to our main file on line 2. You guys see that? Main 2. Okay, so if you have a file that's 500 lines long, it will tell you the error is on line 50. Very useful. Okay. Sometimes it'll just spit out like 5 paragraphs of garbage, and you have to figure it out, scroll back up, look through, and see you forgot a semicolon, you misspelled a variable, right? These things happen. This is your clue into that world. This and the live debug mode, right? If it actually does manage to compile, but it's doing weird things, that's where you use the live debug mode. I really want you guys to be using it as much as possible. Okay, you're pretty much flying blind otherwise, and you don't need to be. Okay. All right, good stuff. So we are going to go back to here. That's all I wanted to talk about for now. This is starting to get into the greater field of like PLC control, right? Your education in why PLCs are used and useful. Okay. The general term for this is called process control. Okay. How easily can we take inputs and affect outputs to whatever we want them to be, right? The accuracy with which we do that, the speed with which we do that, the lack of an error, right? Overshoot, undershoot, all that good stuff is process control. And it's a whole field, a whole science. You could take whole college classes on this stuff. But it's just a small component of what we're going to be talking about in this class. Process control is really term heavy. Okay, I would highly recommend that you guys use vocab cards for this. Okay, if these terms are new to you, if you've never heard of a critically dampened system, then I want you to use flashcards, pretty much. That's the litmus test. If you've never heard of a critically dampened system, you need to learn some new terms. Okay, pretty vocab heavy. So really, what we're talking about is how does a system respond to changes, right? How accurately can we track those changes, and how can we respond in order to make our system do something? Okay. There's many different ways that we can do this, but there's two primary kinds of process control. Okay, open loop control versus closed loop control. Okay. The reason why there's two different types of control is essentially cheapness. Open loop controllers don't need as many sensors. It's not as involved. Okay, you can essentially run something at the speed that you think it needs to run at, and it will kind of just go, right? If it goes faster than that or slower than that, you won't be able to tell because you don't have a sensor to counteract that speed, right? So in our car example here, where we have a car running in open loop, that means that someone's pressing on the accelerator and that's it, right? They're not responding to any changes. They're just hitting the gas, and then the change in speed takes a hit because the environment changes, right? And our input is not changing accordingly. Closed loop, we can see that the engine starts to work harder, okay? That we get some road disturbance, we can see that change in speed or the change in torque on the motor and compensate accordingly. The vehicle speed does not change, where the input torque or the amount of power that we use right to get up that hill does change. It responds accordingly. Okay. So another way to think about this is if you have a car and you kind of know from your past experience, if you push this hard on a section of highway, you push the pedal down this far, you'll go approximately the speed limit. Okay, that is open loop control, where if you are in a residential neighborhood, you know that you can be this far on the gas and you'll be going such and such speed. For 90% of use cases, that would probably work. Okay, this happens a lot in industry where 99% of use cases can be solved with an open loop or closed loop solution. It probably will be. Okay, but in our closed loop, it falls apart in situations where dynamics change. Right, if your system changes at all, if you encounter wind, if your tires are if the tread on your tires is worn out, or if you have to take a detour, any change in your environment will change, not be able to be responded with your simple heuristic, right? If you have a heavy wind against you and you're going as fast as you usually are, you're probably going a little bit more slowly. Okay. So what we do is we try to respond to that error. If we see that the car is slowing down because we hit a hill, or that we see that the car is slowing down because we hit some wind, we can increase the accelerator, right, respond, and restore the state close to our set point. Okay? This, what I'm describing here, the name of the game is error reduction. Okay? Process control, controlling a process is driving the error to zero, if you've never heard that term before. Mathematically, a lot of these algorithms literally are like ways to reduce some number to zero. And that number is how far off of our mark are we. Okay? So there's lots of different ways to do this. Okay, it's a whole field on how do we take some inputs, do some math on them to get the appropriate outputs. It's a very complicated field. Some ways that we're going to be going over in this course is PID, peripheral integrated integral and derivative, proportional integral and derivative control. Okay, PID controller. We're going to do some really simple process control, so-called bang-bang controllers, turning things on and off to get what we want. And we're going to be using hysteresis controllers. Okay. I'm going to be going over what all these things are and why they're useful in a second, but I just wanted to get these terms into your guys' brains. Okay. I would love if you could, again, if you've never heard the term PID before today, please spend a couple minutes to look it up. Okay. YouTube short, TikTok, whatever. We're going to be going over a video in class today, so we will be handling that, but it's a whole thing that we're talking about here, and there's not enough time to cover it. So please look into it some more if you can. Okay. So terms to remember in terms of what we're talking about here: open loop versus closed loop control. Also very cool, worth looking into. Error reduction. I want you guys to know these terms: overshoot, undershoot, steady state variability, rise time, fall time, step time, response time. Okay? All these are very important. I'm going to keep going because, again, this is on Blackboard, so feel free to look it up or just have it up on your computer. This is PID. We're going to go over it in a second. But again, I just want you to know the term. This is bang-bang control, on-off control. And lastly, hysteresis. Okay, hysteresis is a very interesting topic. More of a technique, really. That's got some very clever history behind it, too. We'll go over that in a second. All right, anything I missed? Okay. Feeling good. All right, we're going to do PID, and then we'll continue on to the lab, I think.
Welcome back to Control System Lectures. In this video, we're going to begin our conversation on PID control. This video is just an introduction to the topic and will hopefully provide some good background information on PID controllers. Now, to describe what PID control is and why we use it, let me first describe more generally what a controller is. And one way to write an open-loop system is like this, where inputs act on a plant or the system to be controlled, and then some output signal is generated. Often in these open-loop scenarios, the performance of the system isn't good enough to meet your requirements. Let me give you an example of what I mean. You're tasked to build a robot that needs to move from this spot here over to this red X. You could figure out how fast the robot moves, and then from that determine how long the robot needs to drive for before it gets to the red X. This type of commanding is called open loop, because the amount of time the robot drives is not adjusted based on the actual position of the robot. And open loop commanding is perfectly fine for systems that don't change much or where accuracy isn't as important. However, what if there's some dirt in one of the wheels and the robot veers off to the side? Or if the robot's slightly faster than you had predicted? In both of these cases, the robot won't stop on the red X because it has no way of compensating for these errors and making adjustments on its own. Now the solution then is feedback control, which essentially means you're sensing the output of the plant and feeding it back so that the system can make adjustments accordingly. Now in a feedback system, there's a reference signal, and this is the desired value or the ultimate goal. And you compare that to the measured value, and what you're left with is the error or the delta between where you are and where you want to be. So in the case of the robot, the error would be the difference from the reference position, which is the distance from the start to the red X in meters, and the robot current position, which is measured by the robot, also in meters. So at this point, we need to figure out how to convert an error signal that has units the same as the output of the plant into an input signal that has units that may or may not be the same as the output. And in addition to just changing the units, the error needs to be adjusted in such a way that the input into the robot causes it to eventually reach the red X. And this is exactly what a controller does. It takes the error signal and converts it into a command that is then sent into the plant. And one of the goals of a control engineer is to design this controller so that as time progresses, the error, or the difference between the current location and the goal, is driven to zero. And zero error means that the measured position is exactly where you want it to be, which means that the system meets all of its requirements, well, at least this particular one. Now, there's many types of controllers, and we're going to touch on a lot of them as these videos progress. However, in this lecture, I'm only going to talk about PID controllers and its variations. I'll explain what I mean by that in a second. The PID controller is a great place to start because it's simple, efficient, and effective in a wide array of applications. In fact, it's the majority of controller types in industrial applications, so it's well worth learning. Let me start with the term PID. PID is an acronym, and it stands for proportional, integral, derivative. And each of these terms describe how the error term is treated prior to being summed and sent into the plant. In one of its block diagram forms, a PID controller can be written like this. In the proportional path, the error term is multiplied by a constant Kp. In the integral path, the error is multiplied by Ki and then integrated. And in the derivative path, it's multiplied by Kd and then differentiated. The three paths are then summed together to produce the controller output. Now the three K terms are called gains, and they can be adjusted or tuned to a particular plant with a defined set of requirements. And by changing these values, you're adjusting how sensitive the system is to each of these different paths, either the P, I, or D path. Let me explain what I mean with a few plots here. Let's say the error in the system is changing over time, like this red line. In the proportional path, the output is the error scaled by the gain Kp. So you can see here that when the error is large, the proportional path will produce a large output. When the error is zero, the output in the path is zero, and when it's negative, the output is negative. In the integral path, as the error moves over time, the integral will continually sum it up and multiply it by the constant Ki. In this plot, it's easy to see that the integral path is the area under the curve, where this blue section is positive area and this green section here is negative area. Now, the integral path is used to remove constant errors in the control system, since no matter how small the constant error, eventually the summation of that error will be significant enough to adjust the controller output. Now, in the derivative path, it's the rate of change of the error that contributes to the output signal. When the change in error is moving relatively slowly, like it is at the beginning here, then the derivative path is small. And the faster the error changes, the larger the derivative path becomes. Now at this point, you can just sum up each of these three paths and you've got the output of a PID controller. But you don't always need all three paths. You can remove a path completely by setting its associated gain to zero. When you do this, you generally refer to the controller with the letters of the path that are left. For example, you can have a proportional integral controller, or PI, if you set Kd to zero, and just a P controller if Kd and Ki are both zero. So why would you simplify the controller like that? Why not just make the biggest, best controller you can with all paths intact and super complicated? Well, typically when I'm designing a control law, I try to make the logic as simple as I can while still meeting all design requirements. I do this for several reasons. One is a simple controller is easy to implement. Two, a simple controller is easy to tune, test, and troubleshoot when there's problems. And three, a simple controller is easy for other people to understand, which is important when you work in a large project and interface with other groups that have to buy into the control logic. For example, a software or hardware team that has to implement it. So simple controllers can save you time and money over the life of the program, as long as they still meet your design requirements. And this is why, despite having a lot of really complicated control systems out there, the majority of industry still uses PID controllers or some variation. Now you're probably thinking right now, all right, you've given me the definition of a PID controller, but that really didn't help that much. Because if you're like me, I don't usually understand something by definition alone, and I need some examples for it to sink in. But I want to end this video here so that it doesn't become too long that you lose interest. But next week I'm going to have a video that runs through a thought exercise on PID control, and then shows some of the math to back up that exercise. Now I'm going to link a video here in this box once it's complete, so you can just click on through. If this box is empty, that means I haven't finished it yet. So if you don't want to miss it and you haven't subscribed already, don't forget to hit the subscribe button. And thanks for watching.
All right.
Welcome back to Control System Lectures.
So that was a brief overview of PID. We'll come back to it because it'll be more relevant when we're actually controlling things like temperature, for example. Getting temperature up to temperature quickly without taking forever and not overshooting and boiling or baking whatever you're trying to heat up is a very critical and important thing to learn. For now, we're going to go and do more.
Welcome back to Control System Lectures.
Yeah, we'll do one more video, and then we will do the lab, and then we'll be pretty much it for today. Until 8:30, you'll have time to complete the lab. Ask me questions as you'd like. Yeah, we'll go over that in a little bit. Any questions on what we've seen so far? Make sense? Okay. Cool.
I'm going to continue discussing PID controllers by walking you through a thought exercise that's commonly used to explain PID control. During this example, we'll try to use reason and logic rather than math to see how PID controllers and their variations are used to generate the desired system response. For this example, you're driving your car, which is the plant, and you use the gas pedal to control the velocity of the car. We'll call the angle of the gas pedal theta, where the angle of 0 is when your foot isn't pressing on the pedal. Now I want to create a real simple model of the car to work off of so that if you want to verify our results of this exercise on your own, you can. We need a transfer function from the gas pedal position to the velocity of the car. Now in real life, this is a complicated nonlinear transfer function that's dependent on the car model. However, you can simplify this model by assuming it's just a first-order low-pass filter. And the transfer function for a low-pass filter looks like this, where the output is velocity and the input is angle. So let me explain why this is a reasonable estimate. If you press the gas pedal down halfway, the car would start to accelerate and then eventually settle at some constant speed and stay there. And I can say that any position of the gas pedal, if you held it there long enough, would result in a constant velocity that corresponds to that pedal position. And if you pressed it down just a little bit more, then that speed would increase a little bit faster. But here's where the low-pass filter comes in. If you press the gas pedal down slowly, which is the red line, then the car will be able to change its velocity according to the pedal position, the yellow line. But imagine if while you were driving, you started pumping the gas pedal all the way down to the floor and back up. The car wouldn't have enough time to respond to that, and the velocity would stay relatively constant. Therefore, low-frequency inputs are passed to the output, whereas higher-frequency inputs produce an output that is much smaller. And this is the signature of a low-pass filter. But our model isn't complete at this point, because no one drives by knowingly putting the gas pedal at a specific angle. You don't think to yourself, I need to go 20 miles per hour, so I'll put the pedal at 10 degrees. Instead, people drive by applying a change in pedal angle. For example, you realize you're driving a little slow, so you change the angle of the gas pedal by pressing it down a little bit more. So our command is actually change in angle over time, which can then be integrated to produce an angle, which is the input into our low-pass filter. So the transfer function
Okay.
for the change in
So there's good conceptual stuff in here, and there's some higher level math that's probably a little scary that I want to talk about first. Because sometimes people coming into my class don't know what derivatives and integrals are, which is okay. Like you've never been through differential equations or anything crazy like that, it's fine. But you do need to understand a couple of key concepts from math. Okay. Imagine this is some input signal. Say it's like speed over time from our car, okay, or from our speedometer. This up here might be like 60 miles an hour, and here's our 0 miles an hour. Okay, so in real life, we could check in on our speed like infinitely many times per second, right? 1,000,000 times a second, we could check in and put a dot on this chart at what speed we're currently going at, right? But in real life, we check in much less frequently than that, right? Maybe once a second, for example. So for this second, we are at this speed. I'm going to draw a bar right here. Okay. The next second, the next instant that we're capable of measuring, we are now at this speed. So we have a bar like that. Okay. And then we keep going, just like that. Each of these are square. Okay. So it's not a perfect fit. Okay. There's a little bit of like error here that's not accounted for. Okay, but we're pretty close in terms of recreating this drawing. Okay, give me a second. Keep going. Pretend these are all the same width. Okay, our sampling rate is the same. Doop, 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 doop. Okay, so one instant in time, this slice right here. Okay. Imagine if we took this slice, this chunk, and we made it infinitely thin. Okay, it's like paper thin, super teeny tiny thin. Okay, this idea, this slice of a greeter hole is a derivative. Okay? If we take infinitely thin slices of a signal like this, push them all together, and see how much area it takes up if I were to fill in every single one. Okay, for example, if I say how much colored area would there be in square inches underneath this curve? Okay, and the way that I do that is by taking the height of each of these. So this has a height and it has a width. They're all the same width, right? So we multiply this height by this width. Height by width, height by width, height by width, height by width, and that gets the area of each of these things, right? If you add up each of the areas of these bars, we get the area under the curve. Under curve. Okay, not so scary of a concept, right? Is all we're doing is totaling the amount, multiplying the area under the curve. Okay, but this is the scary math concept, the integral. Okay, an integral literally is the area under a curve. Like mathematical definition, like what an integral is. Okay, when we care about power, energy expenditure, right? If we're tracking power use over time, at one instant we're using 50 watts, next instant we're using 100 watts, right? In order to understand how much energy we use over time, you see that wattage by the amount of time you're using it, right? It's the same thing. So if you took a graph on the instantaneous power that you were taking at each second, and then you took the area under the curve of that, you would get the amount of energy you used. It's the integral of, dx. You guys have seen this funky math term before? Okay, scary stuff. Whole classes are taught about these things, but the things that I want you to remember conceptually is that a derivative is an infinitesimally small slice of something, okay, usually an incoming signal, And if we add all those up, if we take the areas of all of those infinitely small slices and add them together, we get an integral. Okay? So it's going to come up a couple times. He's going to mention things like derivatives, integrals. Okay? What he's really talking about is this, the area under the curve, for example. Okay? This comes up a lot in the I in PID stands for integral. Okay? So literally, definitely relevant. Okay? The reason that this matters is because sometimes we have a very, very small signal, or a very, very small error. Sorry. For example, if we have a tilt platform, okay, where we have this robotic arm, okay, we have a little actuator here, and it's holding this stick upright. Okay, the goal is to hold this stick exactly upright. So if we push on the stick, we push left, we push right, the motor will extend or retract accordingly, so this angle will be 90 degrees. Okay? Say it's off a little bit. The motor is rusty, doesn't have enough oil, there's wind, it's windy, whatever. And for some reason, our control system is not quite getting us there. We're at 89 degrees all the time. We're constantly off by 1 degree. But our control system isn't responding strongly enough to overcorrect, right? It's just like the amount that it's responding is enough to get it to there to 89%. It can't quite bridge. It's not quite different enough to get the extra nudge that it needs to. So the I controller, the integral, is what if we added up that little error so it started to accumulate. So over time, hey, we've had this error for a really long time. Maybe that's important. Okay, that's kind of what this term is doing. So if this little error is here, and if that little error is still here, and if that little error is still here, it will integrate and integrate and integrate and integrate. So our I term, the thing that's saying, hey, we need to correct our action, grows and grows and grows and grows while that error is still there. Okay? Does this kind of make sense in terms of an integral? Kind of? Okay. Complicated topic. I'm probably not doing it justice. Feel free to, please, again, whole videos on integrals and derivatives, like, explain like I'm 5 all the way up to college graduates. So, feel free to look up the resources that you think would be appropriate to you and whatever your last math course was, right? Everyone comes into it a little bit differently from different backgrounds, and there's different ways of explaining it too, different knowledge domains. I'm sure there's one out there that'll make it click for you. Okay, so I'm going to keep it playing. If you guys have any other questions, any terms you don't recognize, please let me know. Okay, I've been out of school for a while, so I work with this stuff all the time. It kind of goes over my head sometimes that I take it for granted. So if you guys are blanking on something, please let me know. Okay? All right.
The gas pedal angle to the velocity of the car is then combined and would look something like this. So keep this model in mind as we go through the exercises. In this first example, we're going to go over proportional control. The closed-loop control system for our car with a proportional controller would look something like this, where the error is the difference between our reference command and the measured signal. And the error is fed into our proportional controller. Now imagine that you're sitting in your car stopped at a stoplight, and the speed limit for the road that you're on is 25 miles per hour. The light turns green and you begin to press on the gas pedal to accelerate up to the speed limit. Now in real life, as you drive your car to respond to this step command, you're unknowingly performing proportional control. Here's what happens. Initially you're commanding 0 miles per hour, and once the light turns green, your reference signal steps up to 25 miles per hour. At this point, you have an error of 25 miles per hour. And this is a large error, so you apply a large change in the gas pedal proportional to that error, and you press the pedal fairly fast because of that. Now, as your velocity increases towards 25 miles per hour, your error gradually gets smaller and smaller, so you gradually slow the rate at which you press the gas pedal. And eventually the car reaches 25 miles per hour, and since the error is 0, you stop adjusting the pedal and you hold it constant. Now at this point we can reason that with proportional controllers, the steady state error will be 0. So with that in mind, try to imagine what would happen if the gain was too large in this example. Now initially the vehicle is at rest, and then the light turns green and there's a step up to 25 miles per hour. Same as before. And this is a large error, and instead of pressing on the gas pedal slightly, you floor it because of the high gain, and before you have time to register that you've pressed the gas pedal too far, your car is all the way up to 50 miles per hour. Now at this point, the error is now minus 25 miles per hour. So you slam on the brakes, and again, before you have time to realize your speed, the car has stopped. And then the cycle starts all over again. And by increasing the gain, you run the risk of making your control system unstable. Perhaps you or someone you know already drives like this, where they apply too much gas or too much brake all the time. If that's the case, then you can tell them that maybe their gain is a little bit too high. Okay, so let's look.
All right, so going back here, I really like thinking of control system examples in tilt controllers. Okay, kind of like what I just talked about before. Imagine we have a table. This is kind of like the inverse of what we were talking about before. We want to keep this table perfectly stable. Okay, we have a little motor actuator here, okay, that we can make go longer or shorter, and the goal is to make this perfectly at 90 degrees. Okay, that's the goal. If we are only to use just if it wasn't clear, you can use a PID controller. You can use portions of it if that's useful to you. Okay, you can use just the P, just the I, or just the D to do what you need to do. Or you could use all three, or even just P and I, or I and D. They're called PI controllers, ID controllers, PID controllers, PI controllers, and all the combinations of those things. Okay, we're going to go over the behavior and what each P, I, and D does, but each of it helps to coax the signal back to where we want it to be faster, essentially. Okay, so we're just talking about the P, the proportional in our PID controller. Okay, so the proportional controller, if I push down on this table, okay, or even let's just say the table starts off tilted already. Okay, it's already like, I don't know, unbalanced, and we have a large error here, right? This is not 90 degrees. We need to put force on the motor to get this side to swing up. Okay, the force with which that motor moves is proportional to the difference. Okay, see this angle right here? So this is our set point, and this is where we currently are. Okay, right? That's our error, E. Okay, here it's an angle, right? Degrees, might be radians, might be a speed value, whatever units we're working in. Okay, so this is our error. Now this is where we're talking about the gain that he was talking about before. Okay, it's literally the thing that you multiply E by to see how hard we should push the other way to correct that error. Okay, so this is our example before. If we know that we need, for example, 50% power to correct for this much difference, we can set our gain to 50, right? It won't actually be a percentage, but you would have to essentially dial this in to give the right proportional response, right? This is, again, literally a proportional controller. If we have an error of this much, we're going to push this hard as given by our gain factor to correct it, okay? The downsides of this is you could totally push too hard and overshoot, okay? So what they're saying would happen here is, say we think we need to give 50% power, but we actually needed to give 30%, okay? And we swing wildly high. We're now here, and the error is in the other direction, okay? We're overzealous in our movements. So now we have an error here. We are going to run the other way, run the motor in the other direction. It's going to swing back, and it's probably going to overshoot again, right? Going to be too overzealous, and then it's going to keep chasing a target it'll never actually be able to reach. Or if it does, it'll be like instantaneous, it'll be gone again. It'll still be chasing it. It's called an oscillating system. Okay? These are the pitfalls of tuning a system and why we do PID tune. Okay? Does this make sense so far for the P parameter and proportional control? So we can actually make this in structured text. Again, each of these systems, P, I, and D, can be implemented in just like a couple lines of code, where it's literally the angle we are minus the angle we should be at times our gain factor, for example. Okay? That would be the simple proportional case. And we're going to go over the integral and derivative here. Again, if this doesn't make sense by the end of this lecture, please look up additional resources. Okay? I'm not going to sit you down and say, program a PID controller. Okay? But I would like you guys to intelligently be able to talk about PID controllers, right? If I say, what is an integral? I want you to be able to give me the concept of an integral back. Okay? I don't want you to be able to solve one, right? Do a differential equation on the spot with a pen and paper, but I want you to have good intellectual understanding of the concept. Okay? All right, let's keep going.
Maybe their gain is a little bit too high. Okay, so let's look at another example now. This time, let's add the derivative term to the control system, but we'll change the problem just slightly. It's the same story as before, where you're sitting at a red light, but now there's another stoplight just down the road that's also red. In this example, you're trying to control your position instead of speed, so that when your light turns green, your reference position, which is where you want to be, steps up from 0 to the position of the next light. In the block diagram, this would equate to adding an integrator right here at the end to convert from velocity to position. And so now this is the new transfer function for the system.
Yeah, don't worry about transfer functions. That's for like.
Also, your reference signal would change from
kind of
speed
engineering
to position, since this is what you're trying to control. So now let's apply a proportional controller to that and see what happens. Again, your reference position would step up to the position of the second stoplight. And since initially your error is large, you apply a large proportional change in pedal angle. The car begins to accelerate, and as you get closer to the stoplight, the error gets smaller and smaller, and the magnitude of the change of pedal also gets smaller. Eventually, you arrive at the light, and right when you're there, the error goes to 0 because you're at the position you want, and you stop changing the angle of the pedal. So everything's okay, right? Wrong. Not only do you have all that acquired speed, but you're still pressing the pedal down, and you blow right past the light. Now, once you pass the light, the error begins to grow negatively, and you start releasing the pedal, and eventually you put the car in reverse and start heading back to the light. But you have the same problem in that direction, and you end up just oscillating back and forth. So the next time you run a red light, you can just tell the officer that you only ran it because you drive with a proportional controller, and that's just what it does. Of course, more than likely, the officer will just say, tell that to the judge, and is going to hand you the ticket anyway. But you can avoid all of that mess by using a proportional derivative controller. When you add the derivative term to the controller, making a PD controller, you're adjusting the change in angle of the pedal based on the rate of change of the error as well as the magnitude. In other words, you recognize that you're closing in awfully fast on the light, so you better start releasing the gas pedal a bit early. It works like this. At the beginning, you have lots of error, and you aren't moving, so the proportional path is large and the derivative path is 0. Once you start accelerating towards the second light, the error gets smaller, but is still positive, so you continue to press the pedal further, but more slowly than you did before. In addition, you're starting to close in quickly on the second light, so the time rate of change of the error is getting more negative. The result is that the derivative path causes you to slow the change in pedal angle. Eventually, the error is small enough that the proportional path contributes less than the derivative path, and you start to slow the car down, and this occurs earlier than your reference position. And if you've tuned yourself properly, which loosely means that you know how to drive, then you're going to stop right at that second light. Now, one way to think of the interaction between proportional and derivative is that the proportional path tries to get you to the destination as fast as possible, while the derivative part is trying to restrain you from moving too quickly. In this case, it takes the balance of the two to properly stop the light. Finally, let's put the entire package together and look at PID control. Let me quickly rewrite the closed-loop control system here so that we have a starting point for what I'm about to say. Now remember at the beginning I said no one drives by commanding an angle to the gas pedal. Rather, they drive by commanding a change in the angle. Well, in this example, we'll command an angle, and I'll show you why that's not a good idea. and then I'll show you how PID control can help in that situation. Let's say you're in your car and you're trying to drive right beside your friend who's moving at a constant speed. In this case, the reference signal is the position of your friend. If the output of the controller is a pedal angle, it's easy to see that there's going to be a steady state error, and you will always trail behind your friend and never beside him. Imagine this. You're some distance behind your friend and you're both going the same speed. In that case, you have an error signal that looks like this. And since the error isn't changing over time, remember that your speeds are matched, the derivative path is 0. And let's assume that the error in the proportional path causes you to press the gas pedal down to its current location. In this situation, you're not going to move the pedal at all, and you'll continue to drive behind your friend, since your velocities will still be matched. So now you might be thinking, maybe your proportional gain isn't high enough. If it was, you could go a little bit faster and catch up to your friend. If you increase the gain, then the proportional path will cause you to press the gas pedal down to a new lower position. And you'll drive a bit faster, catching your friend. However, as you get closer, the error gets smaller, and so you begin to release the pedal, causing the car to slow back down again. So by increasing the gain, all you've done is shorten the distance between you and your friend, which is the steady state error. But you haven't removed the error. You can easily see the flaw in this thinking by assuming you started out at the exact speed and location as your friend, and you use a PD controller. In this case, both the proportional and derivative error terms are 0, so you immediately release the pedal and start slowing down. So by controlling pedal position and using a proportional derivative controller, we have no way of bringing the steady state error to 0. Now this is where the integral path comes in handy to remove steady state errors. When you are trailing behind your friend and the error is constant, the integral path will slowly build up error, adding more and more pedal to the output. It works like this. The error starts out constant just like it was before, and just like before, you're holding the pedal exactly where it already is, and you're trailing your friend. But since the error term is non-zero, the integral path is summing up that error over time and gradually increasing the pedal's position. Eventually, as you close the gap with your friend, the proportional term will be 0, since there's no error, you're exactly equal with your friend. The derivative term will be non-zero since you're closing the gap with your friend, but if you're closing slow enough, it won't have much of an effect on the output. But the important thing is that the integral term is going to be held constant at the exact pedal position that you need. And this is how all three terms are used to control a large variety of control problems. And I use this car example to illustrate it because most people can relate to it, and you can actually imagine the system reacting to different controllers. But keep in mind that these examples are analogous to many systems in real life. If you have a good understanding of the dynamics in the system, then it's possible to reason through the problem to determine what type of controller you need. However, choosing a controller is only part of the solution. You now have to tune the controller in order to meet your system requirements. And in these thought exercises, we really only looked at one of those requirements, and that is whether the error in the system eventually reached 0. However, in a real system, you tune the controller for much more than that. For example, you might be concerned with overshoot or rise time or settling time. And I'll cover how to tune PID controllers in future lectures, and we'll touch on each of those requirements and more. But for now, I hope this gave you a little bit more intuition on how each of these three paths in a PID controller contribute to the overall control system. And as always, thanks for watching.
Okay, so hopefully that was more enlightening than it was confusing. Again, please look up at least one more PID video for soft homework, because again, there's like a dozen of them out there, and each creator goes through it differently. One might, it just takes one to make the light bulb go off. Okay, it took me a while to get this too. I had to go through this class when I went for my undergrad degree, and it did not click immediately. I'll tell you, it's a difficult concept, PID. So take some time with it. Make sure you're comfortable with the concepts. One thing that I do want to clarify before I turn you loose is my explanation of differential, or dx. Okay, this is going to bother me than it will you. I'm going to make it fast. What this actually is, this dx, okay, this derivative, this differential, is the change from this point to this point. Okay? It can kind of be thought of as the slope of these points. Okay? So if this went like this went like this, and this, and this, and this. Okay, so what we're actually looking at here is the change in each of these points. Okay, so this would be like 1, this would be, you know, half, and that would be a change of 0. Okay, or say that this would be a change of 2, this would be a change of 1, this would be a change of 0. If this point was exactly the same as this point, the difference between this point and this point is 0, right? If this point was here, the difference is 1. If this point was here, the difference would be -1. Okay, that is the dx here. Okay, so when we have a term like this, or a continuous signal like this, and we're sampling it, right? The dx is the slope at each of these points that we turned it into a number. Okay, so at this point, okay, this number is the slope at this point. Okay, it's not whatever this value is. So here, I'm going to actually look up a video that I saw in undergrad. Because again, I want you guys to have a good foot forward. The essence of calculus. Yes, 3 blue, 1 brown. Okay. Incredible channel. You can watch it at, you know, time and a half speed if you want to.
Rasmussen has a really good online.
This guy has awesome visualizations. Math visualizations is like his thing. So cool. So it will kind of show you visually what we're talking about for integral and derivative. And then if you have that understanding in your brain, PID will make a lot more sense, okay? Because the I is literally like integral. The D is literally derivative. They're good concepts to understand for understanding these controllers, okay? All right, so enough harping, enough lectures. I've talked enough at you guys. You've been very patient. I appreciate it. Now we're going to go into the lab on Blackboard. So I want you guys to all go on Blackboard and go to the learning modules, sorry, not course materials, week 2, and then click into lab 1. Okay, so this is a submission, meaning that you guys are going to download the docs. This is our lab protocol. It's going to walk you through the steps that we'll need to do. Follow them verbatim, implement the solutions, and then just like I showed you guys before, where we saved our program, right, it was probably in our users. I think it was C drive users. This is my user. Looking for my project file. I did see that, didn't I? Oh, it was in my documents. There it is. Okay, so there's my lab, right? So please pay attention. We're going to right-click your folder and then compress to zip, right? So this zip folder is what you're going to be submitting on Blackboard. Okay, you're going to drag and drop it into Blackboard, right on that submission link for Lab 1, and then this is what I'm going to be grading. I'm going to be looking through that lab. Does it do what you need it to do? Is the content there? Well, is it runnable, right? Again, like as if you're giving it to your workplace or delivering it as a project, okay? So that's it. You should have everything that you need inside of that write-up in the protocol on Blackboard. You're going to have the rest of the time today and beyond if you need it. Again, if you don't finish today, there will be time in the future, future lab time set aside. If you need to finish work, you can work on it kind of thing. So don't feel too rushed if you need it. If you have questions, let me know. Otherwise, my fingers are crossed. All right, good luck.